please make sure the home address. So you make sure you please give it.
I didn't send it yet. I have to say I'm a week away from work in a cottage in France, so
okay.
I didn't do too much work. I have to say, except.
No, it's just that we'll send you something. We're going to send you something. So
yeah, sounds good.
A little gift for your services. You know, and if you know me, you probably can imagine what it would be.
I don't know. No.
You'll see.
But thank you already.
Not many physics centers send these things.
Hi, well, where is your background?
I'm at home. I'm at the home office.
You used to have a really nice Zoom background, no?
Oh, with the pictures. That's at the office. That's at the university office. This is just at home. I mean, I also have even a nicer one. Oh, hang on. Let me see. We should start.
So we want to see the wine, the real.
The wine. I'll put the wine one in a second.
We don't care about pictures.
I agree. Anyway, okay, let me start since we're all here now. So thank you once again, everybody, for joining us for the online SPICE-SPIN+X seminar series, led here by myself, Javier Finova, and Libor Schmeichel, and Angela Wittmann, that are the scientific advisors here, and Karen Eversociety as well, associated from Duisburg, and in association with the Collaborative Research Center SPIN+X, studying all things spin, led by Martina Schliemann-Burger Hillebrands in Kaiserslautern, and by Matthias Chloe here in Mainz. This is a webinar format, so you would only hear the speaker, and then please, you can write your question in the Q&A or raise your hand, and I will promote you to the panelists to ask the question directly to the speaker. We'll have next week, because I'm away in a review, we will not have a seminar, but the week after, we have Nikolai Spalding joining us for a beautiful seminar on hidden magnetoelectric order, and then we'll continue afterwards as well. Today, we have the pleasure of having Toeno van der Vaart, who is at Delft University of Technology. He graduated from TU Delft itself, but went on for postdoc in Philip Research and Harvard University, and then joined TU Delft. And he gave, I saw this talk that I'm actually showing you here, that he's sharing now with us today. Had the pleasure of seeing it in a recent conference, and I thought it would be great to share with the rest of the community on beautiful work he's doing, proving spin waves in magnetism using electronic spins in diamonds with diamond magnetometry. So with this, I'll stop sharing, and I will ask you to please go ahead and start your talk, and we will turn our cameras off and mute ourselves to give you more bandwidth, okay?
Okay, thank you. All right. Thank you very much for the opportunity to present my work to all the organizers, and particularly to Professor Sinova for organizing these very nice online seminars. So let me grab my laser pointer. So today I will discuss experiments that we are doing in our lab in which we use spin waves. So those are waves in magnetic materials to control spins in diamonds. And a typical experimental situation that we have is depicted here in this sketch. So we have a spin in diamond that we can, for instance, embed in a scanning tip, a scanning diamond tip. And then we bring that spin very close to a magnetic material. And in that magnetic material, we excite spin waves using a gold strip line, for instance. And if you bring this diamond spin into the evanescent field of the spin wave, you can actually use the spin wave for high fidelity control of this spin. And hence the title for my talk, Coherent Manipulation of Spins in Diamond via Spin Wave Mixing. Now first, to give you a little bit of background of where I'm from. So my group is located in the Department of Quantum Nanoscience at Delft University of Technology. So this is a department in the physics faculty, which is about 20 groups in size, and it's divided into 3 themes. quantum matter, quantum sensing, and quantum transduction. And our group resides in this theme of quantum sensing. And the reason is that we use a spin, so a quantum object, to do sensing, in this case of spin waves. And since it's a spin, we call it quantum sensing. But I have to say that the quantum nature of the spin doesn't play a very prominent role in the results that I will show you today. Now, to start, our group is currently presented. Well, it's here. So we have about 6 PhD students and 2 postdocs at the moment. And so this is a group picture. And I would like to acknowledge from the start my theory collaborators, Meerdat, Jaroslav, Gerrit Bauer, and Tao Yu. With that, let me go to the topic of the talk, which is to use spin waves to manipulate spins in diamonds. So what are spin waves? Well, they are the elementary spin excitations of magnets, and a picture of a spin wave is over here. So the coupling between spins in magnets give rise to this collective modes that are called spin waves. And you can drive spin waves by, for instance, applying a microwave magnetic field. They are electron spin resonances in the end. And then if you apply a microwave magnetic field, you can set up a spin wave into a thin film magnet. Now, spin waves play a very important role in the fundamental behavior of magnets. For instance, they are thermally excited as a function of temperature, and thereby they determine the magnetization of magnetic materials. But they are also of technological interest, and a primary drive in the field of spin waves is information processing. And here the idea is that we use spin waves for information transport on a chip. Many groups are working towards this direction, or driven or motivated by this direction. And the idea is that you can you can make small on-chip elements to do logical operations. For instance, here you see a directional coupler where you have 2 magnetic bars, and you send in a spin wave at the top, and depending on the length of the bar and the wavelength, it comes out either at the top of the or the bottom. So this is a drive behind in the field of spin waves, but there is also many interesting fundamental applications. And an overview was given in this recent roadmap on spin waves. And many of the papers or the contributions in that roadmap highlighted quantum applications of spin waves. So trying to go down to the single magnon level is a potential quantum application, where a magnon is now the quasi-particle excitation of a spin wave mode. But you can also imagine that you try to use spin waves in kind of hybrid quantum technologies. For instance, you try to couple 2 spins via a spin wave, try to entangle them via a spin wave. Several research proposals have been put forward in that direction. Another very active research topic is in van der Waals magnets. So van der Waals magnets are magnetic van der Waals materials, and the most famous van der Waals material is graphene. So that's a single layer of carbon atoms, a beautiful crystalline monolayer of carbon atoms that you can create by using sticky tape. And since 2017, you can also make these monolayer magnetic materials. Now, in those van der Waals magnets, very little is known about the excitation spectrum. For instance, what is the spin wave spectrum? How can you control spin waves, etc.? And this is a topic of active research. So today I will introduce the technique that we use to study spin waves, and that is based on the spin in diamond, as I introduced in the first slide. So as a spin wave detection technique, this the unique aspect of our technique is that it detects spin waves by their microwave magnetic fields. So there are already several mainly optical techniques to probe spin waves, and they, for instance, you shine light at a magnetic material, and you look at the frequency shift of the light. So our technique is different. We detect spin waves by their microwave magnetic stray fields. So spin waves generate an evanescent magnetic stray field, and it decays very quickly as a function of the distance to the magnet. So if you want to probe those microwave magnetic fields, you need to bring a sensor very close to your magnetic material. Now we can do that using spins in diamond because they can exist a few nanometers below the surface of diamond, and therefore you can put them right where the magnetic field of the spin wave is very strong. And in fact, the magnetic field of such a spin wave increases exponentially as you go closer to the material. So they can be very strong if you go close enough. Now, as a spin wave detection technique, there are several key features. So like I described, we use the NV center or the spin in diamond to detect spin waves by their magnetic fields. And therefore, we can make use of the fact that such microwave magnetic fields propagate through metals, for instance, pretty good. The skin depth is a micron or a few micron at the gigahertz frequencies that we are interested in. And that means that we can also study spin waves, for instance, underneath metals in gated devices. Now, given that you have a single spin, you can also get quite high spatial resolution because the single spin is a point sensor. So if you are able to scan it carefully over your material, you can make a high resolution image of a spin wave. Now, fourth, it's a sensitive technique, and that's mainly because you can put the sensor spin very close to the material of interest, where the spin wave fields are strong. And it's compared to, for instance, an X-ray setup, it's a very simple experiment with tabletop optical setup. Now, in this talk, I will focus first on introducing the technique. So how do we detect spin waves using a spin in diamond? So that's on the left here, magnetic imaging of spin waves using this spin in diamond. And then in the second part, I will focus on how we can use spin waves to actually control the sensor spin in diamond. And we can use spin waves to drive coherent Rabi oscillations of our detector spin. Now, the key role in our lab is played by the nitrogen vacancy center in diamond. So this is the sensor spin that I've been talking about until now. It's associated with this lattice defect in diamond that consists of a nitrogen atom next to a vacancy in the diamond carbon lattice. It has an electron spin associated with it, and because an electron spin is sensitive to magnetic fields, you can use such a spin as a sensor of magnetic fields. Now, what makes the NV center spin special is that it has a photoluminescence that depends on its spin state. So if you shine a green laser on a piece of diamond and you scan it over a piece of diamond and you look at the red photoluminescence, then if the density of such NV centers is just right, you can see them individually in your photoluminescence microscope setup. And then the nice thing is that each of these dots, each of these spots here, you can now use as a magnetic field sensor. So you can measure the magnetic field at a point in space given by the location of the NV center. Now, if you want to use the NV center now for magnetic imaging, the main challenge is to get the NV centers close to the material of interest. And for that, we developed in our lab two techniques. The first is rather simple. So we call this a wide field imaging technique, where we have a diamond that is full of NV centers, so full of these lattice defects, that we implanted about 10 nanometers below the surface of the diamond, 1,000 NV centers per square micron. And we put that diamond on top of a magnetic film, in this case, yttrium iron garnet, a magnetic insulator. And now we have a layer of sensor spins all over our film. And we can, using a strip line, excite spin waves and try to detect them using our NV centers. Now, the resolution of such a technique is limited by two things. First of all, we have the optical diffraction limit, which is because we are using a large number of NV centers here. And the second is that it's very difficult to get the diamond actually into contact with the sample of interest, which is what you want. So our resolution in this experiment is typically limited by the standoff distance to the NV centers, which is on the order of a few microns. If you want to go to nanoscale imaging, then we have to put a little bit more effort, and we make these scanning nitrogen vacancy center tips, where we have a diamond platform here, which is about 50 micron long, with a sharp diamond needle at the end, and which has a diameter of about 200 nanometer. And then you can have an ensemble or a single NV center even at the very end of this tip that we connect to an atomic force microscope, and then we can make a high resolution image of a spin wave. So how does the detection work using NV center electron spins? I have this slide on that topic. So the key tool that we use is the Zeeman splitting of the energy levels of the spin. The NV center electron spin is a spin-1 system. So there are 3 energy levels, and they split as a function of magnetic field via the Zeeman splitting, as you can see here. And here you can also understand how we can now use this spin as a sensor of magnetic fields. Suppose that we are able to measure the spin splitting using electron spin resonance, that will the frequency at which we see the electron spin resonance will immediately tell us the magnetic field at the site of the NV center. And like I said before, the special thing about the NV center is that the photoluminescence depends on its spin state. So as you shine a green laser on the NV center, you actually continuously pump it into the MSS0 state here. And then when you apply additionally a microwave field, so that's of which the frequency is here on the x-axis, and you hit the electron spin resonance, you will see a dip in the NV photoluminescence caused by the smaller photoluminescence associated with the plus and minus 1 states. Now the location of the dip in frequency space then immediately tells you the value of the static magnetic field at this point in space that is determined by the location of your NV center. At the same time, the dip that you see here has a certain amplitude, and the amplitude is determined by the amplitude of the microwave magnetic field driving the NV center. And this is important because this contrast, so this amplitude of this dip, or this contrast of the ESR dip that you see here, is what we use to image spin waves. So we measure the amplitude of the microwave magnetic fields using the contrast of the electron spin resonance. How do we use it to detect spin waves? Well, I show again here this picture of an NV diamond placed on top of a YIG film. We have a microwave strip line, and then we send a microwave magnetic field, or we use it to create a microwave magnetic field that will excite spin waves in this direction. And then to understand what we expect, then I plot here, I sketch here the dispersion of spin waves, which is the frequency of the spin wave as a function of the wave number. So we apply microwaves of a certain frequency, and then we expect a certain wavelength determined by the dispersion. What we do then is we tune our NV center into resonance with that precise frequency. So now we are exciting spin waves of a certain wavelength that are resonant with the NV center ESR frequency. And then we measure this contrast of this electron spin resonance that I showed you on the previous slide as a function of space. And that's the picture that you see here. So this contrast here basically tells you how fast you are driving this NV spin. So it's a measure for the NV spin rotation rate. And as a function of the distance to the strip line, then we get this oscillatory pattern that reveals the wavefronts of the spin waves. Now, a question I often get is, why do you get a standing wave picture here? And the reason is that on the one hand, we have this traveling spin wave mode that moves away from the strip line. But on the other hand, we apply a second field, so a reference field of the same frequency, which is spatially homogeneous. So we have a traveling wave interfering with a spatially homogeneous wave of the same frequency. And that gives rise to a standing wave in the amplitude of the microwave magnetic field that drives our NV spins. How does this work spectrally? Again, to give a little bit of insight in what's happening here, I plot here as a function of the magnetic field the electron spin resonance frequencies of the NV center. So those are the straight lines. And in the background, you see the spin wave band. You may recognize the Kittel mode, which is the lowest energy spin wave mode in our system here. And then above the Kittel mode, so that's this green dashed lines, there's a continuum of spin wave modes available. And we are probing those spin wave modes along these lines determined by the ESR frequencies of the NV center. And then the wavelength is determined by the distance basically to the bottom of the spin wave band. So we can probe different wavelengths by going to different frequencies and magnetic fields. Now, here are some examples then what we can do. So where we use spin waves to drive NV center spins. So this is a sample where we have two strip lines on a YIG film again, and we use it to drive spin waves into the sample. And when we measure here, so this is an image of the Rabi frequency of the NV centers. So at each pixel here, we measured how fast the NV center spins are rotating. And the cool thing here is, well, there are several nice things that are I find very remarkable here. So first of all, you see this very asymmetric picture. So the spin waves only go down and rather than up. And this is a well-known effect of these so-called Damon-Eschbach spin waves. At the same time, you see that they have these triangular shapes that emerge from our two strip lines. And that's because of the specific spin wave dispersion, which is very anisotropic. But from the point of view of driving NV center spins, the remarkable thing here is that even at 500 micrometer away from our strip lines, we can still get very high NV center Rabi frequencies. So for controlling spins using spin waves, this is really nice because now far away you can drive NV electron spins with a high Rabi frequency, and you can do that over a relatively spatially homogeneous with a spatially homogeneous amplitude. Now, from a point of view of sensing of spin waves, the nice thing is that we can look through metals at spin waves underneath the metals. So that's an example that I show here. So here you see a gold strip line again on a YIG chip. The gold strip line is about 20 micron in size, in width, and we use it to excite a spin wave in the YIG. 200 nanometer of gold, and you can see from the point of view of the microwave magnetic fields, this is so much smaller than the skin depth that you can just very clearly see the spin waves underneath. And this allows you to study the interaction of spin waves with metals. And for instance, here we see that the spin waves damp more strongly underneath the metal than next to it. And that's something that we analyzed in a little bit more detail. So here I show again an image of spin wave imaging, where we use the NV centers to image the spin waves underneath a gold strip line. The gold strip line is over here, it's 20 micron in width, and here we sweep the drive frequency on the y-axis. And you can see that as a function of the drive frequency, we excite spin waves of different wavelengths. Those spin waves damp out rather quickly underneath the gold, and they propagate for very long next to the gold. By analyzing this carefully, we can extract this damping constant. We find that it's large underneath the gold and very small away from the metal. And by doing just electromagnetic analysis, you can extract then what is the conductivity of the gold. So more generally, you can use, say, the interaction of the spin waves with some metal to extract properties of the metal. In this case, the conductivity of the metal, so that's directly related to the skin depth, but you can also imagine that you put more interesting materials on top, like a superconductor or some other magnetic material, a magnetic material on top of the magnet. So that is one application area of our technique. Now let me now switch to some experiments where we use a single spin in this atomic force microscope setup to image spin waves with higher resolution. And here is a sketch of the experiment. So we have an NV center at the end of a diamond tip. We have a strip line, again, on a YIG film, and we use that strip line to set up a spin wave in this YIG film. Now we can bring our NV center extremely close into to the magnetic material, so far into the evanescent stray field of this magnetic spin wave, Now, what do we expect to see in such an experiment? Well, to understand that, I plot here the spin wave dispersion. As I mentioned, the spin wave dispersion is very anisotropic because of the dipolar nature of the magnetic fields generated by the spin waves. So here you see a plot of the spin wave dispersion, so frequency as a function of wave vector in the x and the y direction. And what do you expect then if you excite a spin wave with a strip line that is very broad and is very long? Well, you expect to excite only long wavelength spin waves in a particular direction. In this picture, it would be right here. So the frequency of the drive would set the isofrequency contour of the spin waves with which you are resonant. And then the geometry sets the wave vector that you can excite of the spin wave. So we basically expect just to excite this particular long wavelength spin wave mode. So that's what we probe in the following. Here we measure the magnetic fields of the spin wave that we drive using this strip line as a function of the distance between the NV center and our sample. So here we are still relatively far away, and we see indeed the relatively long wavelength, so about 5 micron spin wave mode that we expected from our experimental geometry. Now we do the same measurement, but we just approach the sample now with our tip. So we bring the NV center closer and closer to the magnet. What do you expect then? Well, the spin wave field as a function of the distance d to the sample should increase exponentially as a function of d. So we expect stronger and stronger contrast of our spin sensor. And that's basically what you see here. So the signal becomes more red. We get a stronger photoluminescence response of our NV centers. At some point, this becomes so strong that we fully saturate our sensor and we need to tune down the power, which is what we do on the next slide. This is just to show that as a function of approaching, as a function of decreasing distance, the spin wave field goes up. Now, the remarkable thing here is that when we repeat this measurement now with the tip in contact and we tune down the drive power, we see a whole bunch of spin waves traveling in all kinds of directions. So that's this image over here, where if you zoom in, you see very clear wavefronts of about 360 nanometer wave length. And then if you take a Fourier transform of this picture here, you recover this H-shaped isofrequency contour that I showed a few slides earlier. So rather than just exciting this single wavelength, this long wavelength spin wave mode, what happens is, what we see actually is that we occupy the entire isofrequency contour with coherent spin waves. Again, the remarkable thing here is that we do the same measurement far away or in contact. Far away, we see the long wavelength spin wave, and in contact, we see this whole jumble of spin waves traveling in many directions. And what we believe is going on here is that there are defects in our magnetic field on which this primary spin wave scatters in all kinds of directions, and that gives rise to spin wave occupation of spin wave modes along the entire isofrequency contour here. Now let me go to this other part of the talk, so where we try to use spin waves to actually obtain control of the NV center spin. Until now, I showed you experiments where the spin wave that we excite is resonant with the NV ESR transition. So that means that we can create a spin wave at the ESR frequency, and therefore we can use that spin wave to actually manipulate the NV center spin. Now, in a sense, this is a very limited technique because we can only detect spin waves that are resonant with our NV center ESR frequency. And we have been working towards ways of circumventing this so that we can drive our NV center at any frequency. It doesn't have to be resonant with the ESR frequency. And the idea of the experiment is sketched here. So again, we have a YIG film and we excite a spin wave that is now not resonant with our NV center spins. So in principle, that spin wave is off resonant and therefore it cannot drive NV center spins. However, what we do then is we excite a second spin wave. So we call this a pump spin wave and a signal spin wave. We have a pump spin wave and a signal spin wave, and they mix, and then the mixing product, they are resonant with our NV center spin, and we show that we can use those mixing products to control the NV center spins. So the goal of these experiments is twofold. On the one hand, we want to be able to probe magnetic materials that have spin wave modes that are not resonant with the NV centers. For instance, some of these van der Waals magnets have very high frequencies. how do we detect spin waves using NV centers is still an open question. Via spin wave mixing, we think we can achieve that. The other one is that you can now coherently control spin waves, NV center spins, by using spin wave mixing processes. And you can actually generate frequency combs of spin waves and use any of the lines in those combs to drive your NV centers. Now, again, what is the challenge that we are trying to address? The challenge is that our NV center spins are very narrow band. So our NV centers can only detect microwaves that are resonant with the NV ESR frequencies that I showed here. And again, here is the photoluminescence response as a function of the microwave frequency. It's very narrow band, about a megahertz or so. Expanding this capability is of some interest commercially, but I think more excitingly, it would allow us to probe high frequency magnetic materials or high frequency microwave oscillators on chip, or to actually control spin systems such as the NV center. So the idea is to use spin wave mixing to convert microwaves to the NV frequency. We have developed two schemes to do so. The first is based on 4 spin wave mixing. And this is a rather complicated picture, but let me try to explain this. So here, the idea is that we drive a so-called pump spin wave into the system that is not resonant with our NV frequency. So the NV frequency is over here. Now the pump spin wave can now decay via 4 Magnon scattering into secondary spin wave modes of different frequency, as long as this energy conservation rule is satisfied. Now, if you just apply the pump spin wave, then you can, via 4 Magnon scattering, you can create magnons at all kinds of different frequencies. But what we do now is we apply a signal spin wave, so a second spin wave, with which we stimulate the decay of particular 4 Magnon process. And thereby, the idler spin wave that we then create is resonant with our NV center, and we can use that to detect the presence of these other spin waves. So here's the experiment. So here we sweep, or first of all, we apply a pump spin wave of a certain frequency that is detuned from our NV frequency, so over here. And then we sweep the frequency of the signal spin wave. And you can see if the pump is exactly halfway between the signal and the NV frequency, then via 4-wave mixing, we are creating spin waves resonant with the NV, and thereby we get a dip in the photoluminescence. And then by tuning the pump frequency, we can expand the NV center detection range over a very large range, up to 1 gigahertz over here. We can take this a little bit further. So now we are generating these idler spin waves that are resonant with the NV center, and we can try to use those idler spin waves to actually drive Rabi oscillations of the NV spins. And that's what you see here. So here we have, here we apply a signal spin wave that is detuned by several hundreds of megahertz from our NV center spin. So in principle, these are so far detuned that they can no way drive NV center Rabi oscillations, but then you apply a pump spin wave halfway, the detuning, and then suddenly you get a nice coherent microwave magnetic field that you can use to manipulate coherently the NV center spins. So that is cool. And so the next thing is that we take this process one step further. So where we create a spin wave frequency comb now. So we apply 2 spin wave signals, a pump and a signal, and then we create at equidistant frequency intervals peaks in the power spectral density of the evanescent microwave magnetic field that we can use to drive the NV spins. Here is a sketch of this process, how it works. So where you see a spectral, say, frequency on the x-axis and then amplitude on the y-axis, we apply a pump spin wave at a certain frequency, a signal spin wave of another frequency, and then the mixing product is resonant with our NV frequency. So that's the picture that I showed on the last slide. You can use that to drive Rabi oscillations. Now you can also drive the NV center spin using higher order mixing products. So for instance, here we have the pump again. The signal will create a mixing product that is halfway, that's not resonant yet with the NV. But then that mixing product will again mix with this pump spin wave and create a mixing product that is resonant with the NV. So you get all these higher order mixing processes that give rise to peaks in the power spectral density. And those magnetic fields you can now use to drive NV center rotations. And then the measurement is shown in the background here. So we plot the photoluminescence of our NV spins as the function of the pump and the signal frequency that we apply. And you see that we can create up to 10th order mixed products that we can use now to drive our NV center spins. Now this is a nonlinear process, so we see some interesting behavior as a function of power. I won't go into that detail today. Now this was the first protocol that we developed to detect spin waves that are far detuned from our NV frequency. We developed another protocol. So the first was based on 4-wave mixing. The second one is based on difference frequency generation. Here the idea is as follows. We again have a pump signal and a signal, a pump spin wave and a signal spin wave. And we and now we look at the frequency difference between those two, and we try to detect that frequency difference using our NV spins. In this case, we tuned our NV spin to a very small frequency, 35 megahertz, and then we applied 2 spin wave frequencies that are detuned by 35 megahertz from each other. And then the mixing between these 2 spin waves will give rise to a difference frequency generation, difference frequency product that will drive NV center spin transitions. So that's what we see here. Here we sweep the pump frequency and apply the signal frequency at a fixed frequency. And then we see that we can now basically when the difference between those two matches the NV frequency, we get a photoluminescence response. So now we are able to detect spin waves that are several gigahertz above the NV center ESR frequency. And this sets the stage now for us to expand the technique towards more unknown magnets. And here we show a very speculative picture just to get an idea of what might be possible. So here, for instance, permalloy or cobalt have higher frequency spectra. So here we plot the dispersion, again, for some different magnets, calculated dispersions. And you can see that cobalt, for instance, has a dispersion in the dipolar regime that goes up to several tens of gigahertz. And now if we apply 2 spin waves within that spin wave band, the mixing product can be resonant with our NV center, and this would allow us to probe these kind of magnets. And for reference, we also plot some of these van der Waals magnets here that we may be able to probe with this technique. So this is the outlook. Probing spin wave mixing in atomically thin magnets. There are many unknowns. What is the ferromagnetic resonance spectrum of many of these magnets? What is the spin wave spectrum? How far do spin waves propagate? Can we control spin waves using gates, etc.? I would like to end by acknowledging the group of people that did this work. Jacopo was the first PhD student in my lab. He already graduated and left now, but he developed this wide field imaging technique of spin waves. Samer and Brecht worked on the scanning probe experiments together with Allard. Aniek and Joris contributed to the spin wave mixing. Michael is now using the technique to look through metals, and Roland and Yufan are working also on spin waves and developing the NV center technique. I would also like to thank my theory collaborators and thank you very much for your attention and leave you with my summary slides. Thank you.
Thank you very much. This is fantastic review. Let's see. I think Felipe is joining in a second. He's going to ask a question. Please raise your hands to whoever would like to ask questions. So Felipe, can you go ahead and unmute yourself and ask your question, please?
Yes, absolutely. Hello, everyone. Toeno, thank you very much for the talk and nice results. I was wondering on this spin wave maps you shown on the scanning probe version. what would be the impact of this sort of like 54 degrees angle of the NV center, and if any other orientations, for example, if having out of plane NVs could help or improve into the detection of such spin waves?
But the question is if other orientations of NV centers would help us expand the technique.
Correct, yeah.
Yeah, so indeed, the orientation of the NV center determines how the ESR frequency of the NV center shifts as a function of an applied magnetic field. So by using different orientations of the NV center, you may be able to tune the NV detection frequency in a different way with respect to the spin wave spectrum than you are with other orientations. So I think it would definitely be an interesting direction to use, for instance, out of plane NV centers, because that would allow you to put the magnetization of the magnet out of plane and study spin waves in that geometry.
Matthias, go ahead and ask your question.
Yeah, thanks a lot. Super exciting results. I have a question about the calculation of the spin wave frequencies for the different materials that you had, like 2 or 3 slides from the end. So some of the trihalides, depending on how many of them you stack, they are antiferromagnetic, ferrimagnetic. So for which, was this for a monolayer calculated, or for which of these 2D material stacks did you calculate the dispersion?
Yeah, indeed. So for the chromium triodides, we took a monolayer, I believe. So a very simple ferromagnetically oriented monolayer with a given anisotropy constant that we so the exact value I don't recall, but it's in the supplement of this this article. But indeed, so it's a kind of a simplified system with a single monolayer. You have some anisotropy constant, and from that it follows the spin wave dispersion.
And so the reason that the iron germanium telluride has such a high frequency is simply the high anisotropy, high perpendicular.
Exactly.
Anisotropy.
Yes. Yeah.
Okay. Good. All right. Thanks.
Okay. Dima, can you please ask your question?
Yes, thanks so much for the very nice talk. Could you say a few more words about the hardware implementation of the wide field imaging part?
Yeah, so it's depicted here. So we sketched here. So we have a diamond that is about 2 mm by 2 mm by 0.5 mm in size, that has NV centers implanted 10 nanometer below the surface, that we put on with tweezers onto a magnetic sample. So then the distance to the sample is, I think in our best case, we had about 0.5 micron we have seen, but typically it's more like a few micron, limited by dust. And then the rest of the setup is a scanning confocal microscope. So we use pixel by pixel excitation, and at each pixel we measure, for instance, the Rabi frequency. Does that answer your question?
Yes, thank you. I was wondering about the gap.
Yeah, the gap, indeed. So this is one of the main uncontrolled parameters, and it's extremely important. So if the gap is too big, because you have this exponential decay of the spin wave stray field, you don't see anything. So it's really dependent on a little bit of luck. And the PhD student that put the diamond used a drop cause technique with some isopropanol to try to push away a little bit of the dust. And then if you're lucky, the NVs are close enough and you can detect the spin waves.
Thanks so much.
Hi, Gisela. Can you go ahead and ask a question, please?
Thanks. Can you hear me?
Yeah, we can hear you very well.
Yeah, thanks for this nice talk. I have a question concerning how far you can go with your technique. If you want to study magnonics, this is maybe more than determining the dispersion relation. In real system, you want to know how the different types of magnons are developing, how they interact, how they hybridize, and how they behave at corners or edges. So how far you can go to get a real image of the dynamic image of the spin waves, and to what extent you can go with the wavelength?
Yes. So I think one aspect of our technique is that it's a relatively slow technique. So if you want to do time resolved measurements, pump probe, for instance, so you excite a spin wave, it's better to use an optical technique because they have like picosecond resolution, say, so then you can really study how spin wave packets propagate as a function of time. our time resolution is limited to how fast we can rotate the NV center spin, which is about 10 nanosecond scale. So on the scale of 100 micron, we can excite spin wave packets and watch them travel. But if you really want to go down to small scales and fast spin wave packets, then we are limited to 10 nanosecond spin manipulation time. Now, what we can do very accurately is measure the amplitude of the spin wave mode that is resonant with the NV. So for instance, if you're interested in the efficiency of spin wave mixing processes, right? So you would apply two frequencies that are not resonant with the NV, and you monitor the mixing product at the NV frequency. That's something that we can do very accurately. And therefore, we can shed light on some of these mixing processes like four-wave mixing and the efficiency of creating frequency comps. Yeah.
And concerning the amplitude, to determine the real amplitude of the spin angle, you need to know exactly the distance of the NV center to the surface. Is this easy to control, or for example, if you have a not so flat system as maybe a Van der Waals system, which some waves inside or so?
Yeah, so with our scanning NV setup, we have the best distance control. So there we have an NV center inside a diamond tip that we can approach to a sample using a piezo. And then we have distance feedback with a tuning fork. So there, the typical distance resolution that we have is on the scale of a few tens of nanometer. So that is about as precise as we can get. If we, for instance, touch down the tip, which is something that we can easily do, then the distance between the sample and the NV center is determined by how deep the NV is in the diamond. Plus, if there is maybe a particle of dirt at the end of the tip. And neat.
Okay, thank you.
Excellent, thank you. From my side, I was a little curious. So, whereas you're looking mostly at ferromagnetic samples, for the antiferromagnetic systems, is that what is the limitation here?
Yeah, so for antiferromagnetic systems, I mean, the challenge is that our technique relies on detecting magnetic fields, right? So if there is no magnetic stray fields, then our technique doesn't detect anything, basically.
Right. But if you have chiral modes, so for example, I'm just probably thinking about the altermagnetism materials that we have predicted to have some chiral modes that should carry angular momentum, to carry some magnetic momentum.
So if you have a slight canting, for instance, between spins, then there are ferromagnetic components to the antiferromagnetic spin wave modes, and those we may be able to detect.
Okay, that will be something to explore. Okay, very good. So is there any further? Oh, sorry. So Yonko has a question. Let me promote him here for a second. One more question. He's joining us. Our loyal editors from PRB. Yonko, can you go ahead and unmute yourself and ask your question, please?
I unmuted myself. Here's the video. Great talk, a rare talk. So I assume what I'll be asking you is kind of tangential to what you're doing, but I sense that it's not a pun. I sense that the sensitivity of your method is such that you can actually do some pretty unique fundamental measurements, especially of those samples with high anisotropy or relatively high, where you can track the temperature dependence of the anisotropy. And this is very rare, especially in two-dimensional materials. And I think I assume all these things were at room temperature, whatever temperature you found best. But if you vary it, you'll see also how going towards the critical temperature, you'll see both the magnetization going down, but also, for me, it's more interesting than the anisotropy, but you can measure both. Often it's considered that anisotropy, in many theories, anisotropy is considered derivative from how magnetization behaves. So my question is then, would it make sense if you develop a sensor to measure the temperature dependence of anisotropy and probably magnetization, or both?
Yeah, no, I think indeed this is one of the nice application areas, so that you can, as a function of temperature, measure the stray magnetic field at a very well-defined distance, for instance, from a magnetic edge in the sample. And that would allow you to determine whether the spins are oriented perpendicularly to the edge or along the edge, or how the strength of the magnetization perpendicularly to the edge changes as a function of temperature. And then this is related indeed to the anisotropy of the system, the demagnetizing energy of the system, etc. So those temperature-dependent measurements can shed light, I think, on that indeed.
Okay, thank you. Well, I mean, after all, the only reason, well, okay, let's call it the only reason you have ferromagnetic order in 2D is that there is anisotropy. Otherwise, Merwin Wagner say there shouldn't be, right? So it's kind of, you may pay tribute to the fundamentals here by measuring the temperature dependence if you wish.
That's right.
Thank you. Thank you.
Yeah.
Thank you. I think that's the end of the questions. I'm going to stop the streaming now.